everyone. So we're back with a couple more lectures about rings here. This is technically Friday's lecture, even though I'm posting it on Sunday. Sorry, and then there'll be another one tomorrow. I'll say all this in the course announcement as well. But we're gonna finish off the rest of this chapter 6 stuff over the next 3 or 4 lectures, and then that'll be the end of the term pretty much. So the next big topic is kind of the theme of constructing one ring out of another, and we're going to start with this major idea of a quotient ring. So let me recall from last time, recall what an ideal is. So recall that an ideal, so if R is any ring, so we recall that I and R is an ideal if 1, I plus is a subgroup of R plus, right? So remember, a ring has plus n times, and under plus it's an abelian group. So certainly you want a subgroup if you're a abelian group. And then 2, R times I is contained in I times R is contained in I. So, in other words, multiplication by any element of R on either the left or the right preserves I. Pretty soon most of our rings will be commutative, so this will be redundant, but you can demand these two, and then of course, if I demanded only one, I would have the notion of a left ideal or a right ideal. I wrote all that out last time, so I won't do it again. I'll just say it in words. Okay, so since R is an abelian group and I plus is a subgroup, we know that R mod I is a quotient group. So we came across this definition. It was natural. It was nice, and so let's note that R mod I plus is an abelian group. Right, I'll just put check mark, because we know that if I have any group and I take a normal subgroup of it, and since this group is abelian, all subgroups are normal, I can form the quotient. I can form the quotient group. So this makes sense. And now we claim that R mod I is actually a ring, that if we define... Okay, so let's take 2 equivalence classes. Let's call this A plus I. So that's some equivalence class in R mod I. So this is a class in R mod I, right? What's a class in R mod I? It's some element. It's the set of all things which are the form some element plus something in the ideal. So we can abbreviate this A mod I, A plus I, excuse me, and then we have B plus I, and then we want to define that to be, well, no shocker there, AB plus I, okay? And so we have to check that this definition is independent of choices. So check. This is independent of choices. This is indep of choices. In other words, what happens if instead of choosing, right, so when we made this definition, it looks like we chose a representative A in the class, the first class, we chose a representative B in the second class, and then this looks like it depends on those choices when we took A times B. So now, suppose you were to modify these choices. So suppose I were to take A plus I1, B plus I2. Well, that's a product, and it's AB plus AI2 plus I1B plus I1I2. Okay, but now the point is, this is something in R times something in I. So this is in I. And this is something in I times something in R. So this is in I. And this is in I. So this is in AB plus I. So it's the same class, right? If I instead of choosing A, I take A and modify it by some element, modify it by adding some element of I, and I modify B by adding some element of I, the answer is exactly the same coset. So in fact, this multiplication is totally well defined on the quotient group. On the quotient group. That's right. So the point is that it's totally fine to define multiplication this way, and this implies immediately that R mod I is a ring. 1 in this ring, by the way, is the class of 1 plus I. So with 1 plus I, 1 plus I as the unit element, 1 plus I as the unit element, this makes R mod I into a ring. R mod I plus times into a ring. So that justifies, I think, in retrospect, hopefully the definition of ideal. I mean, we kind of explained it before, but now I think hopefully it's really clear what it means. It's exactly the thing that you need to make the quotient into a ring. Okay, so Goodman calls this theorem 6.3 or whatever, but that's fine. All right, so let's do some examples. Yeah, he does several of the classic ones here. So z mod n is the basic example. So example, if r is z, I is n times z for some integer n, r mod I is z mod n z. We discussed this as a group extensively, but it's also clear that there's a multiplication on this thing, and we used it, of course, occasionally, making z mod n into a ring. So there's no shock there. Okay, so what are some other interesting examples of this? So let's take a look at some of those interesting examples. So you can take, so maybe that was example 0 or something. So we'll just continue on, just calling them all example. So so now let's consider the case of a polynomial ring over a field. So that's the next. So you have the integers, that's your kind of your basic ring here, and then the next example is a polynomial ring over a field. So let's take, for instance, so he does it with Rx, and we'll do that in a minute. But let's do it with let's start with something over Q, I think, which is a little bit more interesting. So let's take example. So let's take rational numbers, adjoin X as our ring, and now let's take the ideal. Let's suppose that we take a polynomial to be x squared minus 2. Okay, so I'm going to use a fact here, a fact from basic algebra, that the square root of 2 is an irrational number. So in other words, x squared minus 2 admits a factorization, which is x plus root 2, x minus root 2, but that root 2 doesn't exist over q. Okay, so what is this qx? So let's look at qx mod x squared minus 2. So what does this look like? Well, so I claim that it's a I claim that it looks as follows. I claim that it's equal to q plus q times x bar. So x bar denotes the image of x in the quotient. So here x bar, oh sorry, so the ideal is qx times x squared minus 2. So to be clear about what the ideal is, what's the ideal? I take my polynomial x squared minus 2 and I multiply it by any element. Okay, and now x bar is just x plus I. All right, so that's, I'm just denoting this way. So I claim that this qx mod x modulo x squared, this whatever in parentheses x squared minus 2, which is the ideal denoted by x squared minus 2, but I should not be so informal, and I should instead write qx mod I. I claim that this consists of elements that look like a rational number plus a rational number times x, and everything can be written that way. That's it. So it's a in linear algebra terms, it's a two-dimensional vector space over Q, right? So I claim it's this as a set or as a group with multiplication given how. So the point is x bar squared is equal to 2. So, right, so Q has the obvious multiplication. Something in Q times something in Q times x bar is the obvious thing, right? So if I have, so x bar squared is 2. All right, sorry, so that's true, but let me give you the full multiplication table. A naught plus B naught x bar, A1 plus B1 x bar is equal to what? Is equal to A naught A1, okay, plus B naught B1 times 2, right? X bar squared is now been set equal to 2, so plus b naught a1 plus a naught b1 times x bar. All right, so it's a rank 2 vector space over Q, which now has this funny multiplication on it. All right, how did I come up with this multiplication? Well, remember we're taking classes in a world where x squared minus 2 is 0. In other words, x squared is 2. So to come up with this multiplication, you just multiply it, multiply this term out, but now x squared has now become 2. So that's where that comes from. Okay, but then the question is, why is this quotient have only this stuff in it? Why isn't there anything else, right? It's clear that I can take things of this form, but where did everything else go? But the point to remember is that x squared is now 2. So that means that x cubed is 2x. Okay, so let's put it, so x bar squared is 2. So x bar cubed is, well, I just multiply both sides by x bar, so that's 2x bar. X bar to the 4th is 2x bar squared, which is 4, etc. Right? So if I take any polynomial in x bar, I actually only get things of the form rational number plus rational number times x bar. So any polynomial in x bar is contained q plus qx bar. And so since everything in this ring is a polynomial over q and x bar, this is the whole ring. So I've just given you explicitly the multiplication table in this ring. So it turns out this ring is actually a field. And what field is it? It's exactly q, but you throw in the element square root of 2. Okay, so this is a field called, so I'll just note, this is a field called q adjoin root 2. Okay, so that's kind of the basic example of this. If instead of x squared minus 2, I would have put x squared plus 1, I would get I. And so that's how you get complex numbers out of real numbers. And this is the reason I just didn't do that one is it's in the book, but it works exactly the same way. So when I take a polynomial ring over a field and I mod out by some polynomial, or the ideal generated by some polynomial, I will often get another field, and that field will have some interesting relation to the original one. All right, I'll leave that for now. Yeah, okay, good. So they prove an abstract homomorphism theorem for rings, which I'm not going to prove because I think it's easy and kind of boring, and you just, as you work with these things, you just learn it. I think the important thing about taking quotients is the fact that it allows you to construct very general new rings out of old ones. Okay, I do want to talk a little bit about maximal and prime ideals, though, before we move on to quotient rings, which is another interesting way of constructing rings. So let me give you two definitions. I guess I'll start with maximal. I don't know if he does prime in this. Maybe we'll do maximal in this section, and then we'll do prime in the next quick little subsection that we're about to enter into. So an ideal INR is maximal if it's the largest two-sided ideal. So if for any I, j, so anytime you could squeeze j in between I and r, and here j, a two-sided ideal, so anytime you have that, that implies either j is I or j is r. Okay, so it's the biggest possible ideal. In the world of commutative ring theory, this is a very important concept, closely related to the one of a field. So there's a non-commutative version too, but I'll just give you the commutative version. So let me give you a little lemma, the version of which could have been proofs for these are non-commutative rings, but I'll just give you the commutative one. So lemma. Let R be a commutative ring. So R is a field. if and only if 0 is a maximal ideal. Seems kind of weird, but there it is. So in other words, the smallest ideal, which is 0, is actually already the biggest ideal. So the ideal structure of such a ring is basically trivial. That happens if and only if R is a field. Okay, so let's prove that. So proof, suppose R is a field, so let's go this way. So suppose that R is a field. We want to prove that 0 is a maximal ideal. So that means that any ideal that isn't 0 is R. So if R is a field, J in R an ideal, J not equal 0, that implies J equal R. That's exactly what we have to prove. That means that 0 would be maximal. So this is J not equal 0. Okay. So okay, but J not equal 0 is the same as saying that there exists some element, let's say A in J, A not 0. Right? So in other words, you have an ideal and it contains a non-zero element. Okay, so now we use that R as a field. Being a field means that every non-zero element has a multiplicative inverse, right? So this implies that A inverse A, so A inverse times A, which is equal 1, is in J, right? Because what's an ideal? It's something that's closed under multiplication, under left and right multiplication. It's a commutative ring, so it's the same. Left and right multiplication, the same thing. So this is telling you that the ideal contains 1. But now, if R in R is arbitrary, then R times 1 equals R is in J. Right? As soon as my ideal contains 1, I can multiply by anything times 1, and so then my ideal contains any element. And so what do I conclude? I conclude that J is R. Okay, so if R is a field, any non-zero ideal would have to be R, and that says that 0 is maximal. That's the biggest ideal. Let's go the other way. Suppose that 0 is a maximal ideal. Okay, so if 0 is maximal, so I'll just say 0 maximal means that exactly the same thing. If A is not 0, then R times A equals A times R is all of R. Right? This is exactly what it means. If you take any non-zero element, you take any element in R, all the collection of all the elements in R times that element, that's an ideal. And of course it's a commutative ring, so that's the same as take A and multiply by any element, right? So this is a perfectly good ideal in the ring, right? And now so whenever you have an element, you can take the ideal that it generates, R times A, and now since any non-zero ideal is the whole of R, that's R. So R times A is all of R. So there exists B in R such that BA is 1. And that's of course AB since R is commutative. And so this implies that R is a field. Right? Any element had a multiplicative inverse. Well, that's another way of saying field. All right. So that's our lemma, and now let's write a corollary of that, which is the following. Let R be a ring, I and R an ideal, then R mod I is a field, if and only if I is maximal. Right? R mod I is a field if and only if I is maximal. Okay. Why? Because, well, it follows immediately, right? Because R mod I is a field implies that 0 is a maximal ideal in R mod I, but that means that there's no ideals between I and R. And similarly, I is maximal means there's no ideals between I and R. So when you quotient by I, the resulting ring has no ideals between 0 and R mod I, and that means it's a field. All right, so it follows pretty much immediately. Okay, so I'll write the corollary of that. For R Z, PZ is maximal for all primes P. And that's actually an if and only if. An ideal in Z is maximal if and only if it's of the form PZ, right? Because those are the only quotient rings that are fields of the integers. All right, so this is probably not too shocking. Primes are exactly the sort of atomic elements, and so the ideals they generate are the biggest possible ideals. There aren't any. There's no way to factor those out. Okay. All right. So in the last few minutes, maybe, yeah, I'll try to say a quick word or two about what is an integral domain, and then we'll talk about it more in the next lecture. So just sort of in view of this result. So so this result says that if you have a maximal ideal, when you quotient out by it, you get this thing called a field. All right. So this kind of makes you think a little bit. Okay, well, if we're quotienting out by different ideals and we're asking what kind of rings we can get, you know, if you start to think in that vein, you might try to think of kind of, instead of considering quotients that are fields, what sort of weaker structure can you consider? So I'll finish off today by leading you with this definition. So a domain, an integral domain, is a ring, commutative ring. To be clear, this is ring commutative territory here. Commutative ring R, such that if AB is 0, then either A is 0 or B is 0. So in other words, you have some kind of cancellation property. If a product is 0, then one of the elements must be 0. All right, so let me say a few words about this before we go. So let me give some examples. Example, F a field implies F an integral domain. Okay, why is that? Because if you are in a field and AB is 0, so AB is 0 implies if A is not 0, then A inverse AB is 0 implies B is 0. And similarly, if B is not 0, you get A is 0. Right? So if you can multiply by an inverse, of course, then you get this cancellation law. But of course, there are other examples. So example 1, example 2, Z is an integral domain. It's an easy property of integral multiplication. And 3, if R is any domain, so is Rx. In other words, a polynomial ring is a domain. And this is neat. So this is also easy. It's just multiplying two polynomials is just a big sum of multiplications of elements in R. And so if you can just check right away that if the product is 0, then each of them had to have been 0, as long as R had that property. And so for instance, if you start with a field, you take a polynomial ring over a field, you take a polynomial ring over that, you take a polynomial ring over that, you can get infinitely many rings, all of which are automatically domains. So we're seeing there's lots of domains around. It's a nice notion. And now let me leave you today with this definition, and I'll talk about it a little more next time and some other variants on it. Let R any ring, I and R an ideal, sorry, any commutative ring. I is prime if R mod I is an integral domain. Right, so a maximal ideal is one for which the quotient is a field. A prime ideal is one for which the quotient is an integral domain. So I'll talk about this a little bit more next time. We'll dive into it a bit. We'll talk about quotient rings, and we'll do a little more ring theory. But I wanted to just end by presenting that definition in a way completely parallel with the one from before. Okay, this is going up tonight. There'll be another one going up tomorrow night, which is technically Monday's lecture. I'm sorry, we're a day off. And I'll be on Piazza and I'll make some announcements. So I'll talk to you guys. I'll be around and I'll talk to you guys soon. Thanks.